Spin dynamics of the atomic scale nanomagnet. This is the outline of my talk. I will talk about the electronic pump probe spectroscopy, and I will give two examples what we can do or what we can learn from the spin dynamics of the nanomagnets. This is a way how we make the nanomagnets. We just make it by atom releasing on the copper natural surface. And then in order to study the spin dynamics to go beyond the conventional time resolution of the STM, we use the electronic pump probe technique. So the way we do is we send a sequence of pump and probe pulses to the STM tunneling junction. And for the pump, we use the pump probe to, it has is above the spin excitation energy, so it can, by inelastic electron tunneling, it can excite the nanomagnets. And then at some time delay, we also send the probe pulses to the tunneling junction. And then because our tip is also spin polarized, because when the nanomagnet is in different state, so and in the excited state, and then it will have different magnetic resistance. So by gradually varying the pump and probe time delay, we can monitor how the tunneling current changes. And then in this case, we could, by gradually change the delay time between the pump and probe pulses, we can map out the spin dynamics of the nanomagnets. And this technique is developed by 2010 by the IBM group. And this is our machine in Hamburg. We have the unicycle 400 millikelvin STM, and we have the vector magnetic field, which can apply magnetic field 2 Tesla auto plane and 9 Tesla auto plane and 2 Tesla for other directions. So with this machine, with the vector magnetic field, we can precisely align the magnetic field to the any direction we want. And also, like for example, by tracking the IETS, the evolution of the IETS spectrum, we can precisely align the field to the easy axis or hard axis of the atoms on the surface with ±3 degree accuracy. And now I want to give you the first example for controlling the spin dynamics of the nanomagnets. So this is the iron trimer, which is built on copper natural surface. They are anti-ferromagnetic coupled between each other. The coupling strength around 1.1 or 1.2 milli-electron volt. And then if we measure the spin dynamic on these three atoms, you can see the spin contrast can also be seen for the pump probe measurement. You can see on the top, on the two side atoms, the current will first drop and then will recover. But for the center atom, will first increase and then drop back. So if your tip is further away, let's say 10 millivolt, the conducting is 10 millivolt or 20 to 30 picoampere, you will get almost the same lifetime. Doesn't matter which atom you are measuring. So the interesting thing we found is when you are measuring on the center atom of the iron trimer, if you move your tip closer, you will find the lifetime, it will become longer. And then if you put your tip, park your tip on the side atom, and then you still do this measurement and move it closer, you will see the lifetime become shorter and shorter. So for this one, it's easy to it's simple. It's because once you approach more and more, then the lifetime will become longer and longer. So let's see what happens if we keep approaching the tip to the side atom. What will happen once it's going really small? And what we found is if you keep going on this side atom, at some point you will see you can now see the lifetime is already beyond the time resolution of our system is, let's say, below several nanoseconds. And then if you keep going, the sign of the pump probe signal will change. So this we thought this is because we reversed the spin of the trimer because of the interaction with the tip. So in order to, basically this is a measurement, and on the side atom, this is on the center atom, and this is side atom. So in order to understand this behavior, we just use this spin Hamiltonian for the iron trimer. If you diagonalize this spin Hamiltonian, you will see there are two low-lying spin states. The others are like a 7 or 8 millielectron volt higher than the bottom two states. What we are measuring with the pump probe spectroscopy is we are measuring the first excited state relaxation to the ground state. Without magnetic field, these two states are the superposition state of the -2 and +2 state. So once you apply magnetic field, these two states will start to become demix. And then this state will close to +2, pure +2 state, but still have a small amount -2 state. And this guy will become -2 state, but also have some +2 state contribution. And then the lifetime really determined by the relaxation rate between these two states. So if we turn on the interaction with the tip, so what we know is like from the measurement we assume that the interaction between the tip, they are antiferromagnetic coupled. So let's see if your tip interaction is really favors the ground state, and then it moves the state to this direction. That's why the lifetime become longer. So if you move your tip to the side atom, and then it will make the ground state higher, unstable, and then the energy will go higher, and then this lifetime will become shorter. But once you go over this level crossing, then your sign of your pump probe signal will change, and also your lifetime will start to increase again. That's what we observed. And then, as you can see, by changing the tip distance between the trimer, and also you can fully control the spin state mixing of this nanostructure. This is the dots are the measurement, and the solid lines are the calculation by including the tip interaction as a local magnetic field. So by characterizing the interaction, the changes of the lifetime as a function of a field, we can characterize how strong the local magnetic field is, because the lifetime of the trimer is really skewed with the energy splitting for the two low-lying states. And then surprisingly, we can see the local magnetic field can reach 2 or 3 Tesla, even by only one atom coupled to the nanostructure. So in this talk, I talk about we can control the spin dynamics of nanomagnets. And in this talk, I will talk about since the spin dynamics of the trimer is very sensitive to the external perturbation. So I want to use this one as a sensor to sensing the spin environment. This measurement is just done like 2 or 3 weeks ago. So the idea is like in order to turn off the tip interaction, so for all the measurement, we always keep the tip at the same distance. Basically, the tip has the same tunneling conductance. So what we are doing is like, for example, this is our sensor, and there are several surrounding nanomagnets on the surface. So if those nanomagnets spin state changes, so we should be able to detect 2 different decay curve. And then if we fix the time delay, and also when those nanostructures are switching, we should be able to say 2-state switching in the pump probe signal also. So as Sebastian said in his talk, if you put more iron atoms together, they will become the classical magnet. They will have 2 stable Neel states. So as you can see, this is the 2x6, and it has 2 stable Neel states. And then we can also, to study the interaction between these 2 nanostructures, we can gradually move the trimer away from this 2x6. And also we measure the spin dynamics on the trimer for each distance. As you can see, even though they are around, this is 3 nanometer away from each other for these 2 nanomagnets. As you can see, we are still be able to clearly see the different lifetime on this trimer. And also we fix the delay, we can see the two-state switching because of the switching of this big nanostructure. With this, we can basically only measure this, we will know the state of the 2x6. And surprisingly, we can well, you saw these two nanostructures are on the same carbon natural island. Of course, they will interact with each other. Surprisingly, we also built the two nanomagnets on different carbon natural island. You can see here they are separated by this copper braid. Those green area are the carbon natride, and these blue are the copper braid. So we can still, if we measure the lifetime on the trimer, we can still see this. They are interacting with each other. So we can also, like say for this nanomagnets also, you can also detect the interaction between the trimer and the big nanostructure. So and you can, here we want to, so once we know by the pump measurement, we know the lifetime difference for as this big nanostructure in two states. Yeah.
Just a quick question.
Yeah.
As far as I understood, these two Neel states are equivalent.
Yeah.
It's also then with a magnetic field so that you have a higher probability to be one state than the other state, or is it just accidentally that it looks like it's more 80% of one?
No. It is. That's a very interesting question. So for this one, we are doing we can sensing the state of the the big nanostructure, but we are not doing non-invasive measurement. Basically, when your pump pulse can induce the switching of the big nanostructure by the hot electron. Basically, you can try even on the bare surface. You don't need the small nanostructure even you apply pulse on the bare surface, you go back to see it, you still can see the big nanostructure switched. Basically, your hot electron injected by the pump pulse induces the switch. Also, because it's spin polarized, it also favors one state. Yeah. So we can characterize the T1 how it scales with delta E by also measuring the lifetime changes at the external magnetic field. So we know the slope. So in this case, we can get the interaction energy because we know the delta tau induced by the by the big nanostructure, and also we know the slope. So we will know the interaction energy. So the interaction so I want to know what's the physical origin of this interaction. So if I look at this paper, the interesting thing is they calculated the RQQI, the exchange interaction on different different metal surfaces. Like on the copper 111 or 110, they can calculate the oscillatory RQQI interaction. But interestingly, if they calculate the RQQI interaction on the copper 100 and also gold 10, there's no oscillatory behavior. Just the interaction, what they claimed is because there's lacking free electron type surface states. There's no long-range RQQ type exchange interaction on the 10 surfaces. So it is consistent with what we are measuring. So I also, by using this model, I also assume the interaction on the surface, they are just exponentially decayed. So the pink dots are my measurement, and the blue one is the fitting. By assume the exchange interaction, they are just exponentially decay as a function of distance. So the blue curve is calculated dipole-dipole interaction by counting all these atoms interact. So as you can see, the dipole-dipole interaction are still small. So this is by fitting this data, we can get the exponential decay, the exchange interaction on this surface. I want to say is like this distance is the minimum distance we have is 1 nanometer, and then we can go to several nanometer. So now if I put more nanomagnets surround the trimer, and then by the imaging we can see there are 4 states. 4 states because each one has 2 new states. And then we still do this measurement. We do the lifetime measurement on the trimer, and we fix the delay. So let's see what we can get. So we can get here is we can clearly see there are 4 state switching. So you can stop your measurement and image it. You will know which one it is. Also, as you can see, the big jump is caused by the switching of this nanostructure because these two are near each other. So the interaction is strong, and it causes strong jump for the pump pro measurement. Also, this guy, they are slightly further, and then this switching is caused by this nanostructure. And also, this guy is less stable than this one. You can see there are 2 atoms less than the than this nanostructure. So this is how we use it to sensing the surrounding the spin state of surrounding nanomagnets. And this is my conclusion of the talk. And we can control and tuning the spin dynamics of the iron trimer. And we can also revealing the interaction between the nanomagnets. And also we can use it to sensing the spin environment at the atomic scale. I would also like to thank all the group members in SPICE lab. And also I would like to thank you for your attention.